These are fascinating times in mathematics. Chaos, fractals, dynamics, all of these are terms that are very much in the news these days. What I'd like to do today is tell you a little bit about what these terms mean and where they come from. These are terms that come from the area of mathematics known as dynamical systems. I feel that dynamics is a natural topic to expose students to in high school or in college. It's a fascinating area of mathematics. One reason it's so fascinating is because, as you'll see today, the computer graphics images that come out of the field of dynamics are beautiful. There's something in these computer graphics that strikes the human eye as quite alluring. Another reason for the fascination with this field is the fact that it's so exciting. Much of what you'll see today is less than 10 years old. This is new mathematics. One might think then that this area of mathematics would be somewhat esoteric since it's so new, but in fact, much of this mathematics is very accessible. We're talking about quadratic functions, sine, cosine, the kinds of things that students in high school know quite a bit about. Finally, this area of mathematics involves in an essential way the use of the computer. Computers, computer graphics, and computer experiments are essential to understanding and working with dynamical systems. Finally, this area of mathematics promises to be quite applicable. Anyone who's read the book by James Gleick called Chaos, The Making of New Science, will see the tremendous power of this mathematics in terms of applications in all areas of science. Let me begin by showing you a videotape of some of the computer graphics images that come out of this research. The film you're about to see is a film about sine and cosine, a film that I've made as part of my own research in dynamical systems. What you're looking at here is a Julia set. This is one of the terms that I'd like to talk about today. Julia sets are one of the most complicated objects in mathematics and also one of the most beautiful. Notice the intricacy of this image as it changes. These images are produced by a process called iteration. We'll talk a lot about what iteration means, how it applies, and in fact how these images are created using the computer. What you're seeing is the scientific topic known as the collapse of a Siegel disk. No one really understands what's happening in these films. In fact, this film was seen for the first time barely 4 years ago. So let's begin by talking about what we mean by a dynamical system. Basically, a dynamical system is any process that moves or changes in time. As such, dynamical systems occur in every branch of science. For example, the motion of the planets in celestial mechanics. There's a good example of a dynamical system, of a process, of something that's evolving in time. The weather, another system that changes quite dramatically in time. Similarly, the stock market, economic systems. These are good examples of very chaotic, at times, dynamical systems. Finally, in chemistry, simple chemical reactions are examples of processes that evolve in time. When a scientist confronts a dynamical system, the question he or she asks is, can I predict what will happen in the future? Can I predict how this motion will evolve in time? Now, as you look at these examples of dynamical systems, you say, well, some of these dynamical systems are clearly predictable. The motion of the planets, for example. You know that tomorrow morning when you wake up, the sun will rise. Similarly, chemical reactions. You know that tomorrow morning when you put cream in your coffee, the resulting chemical reaction won't be an explosion. On the other hand, the weather or the stock market, those are examples of dynamical systems that seem totally unpredictable. If I knew where the stock market would be tomorrow, I wouldn't be here today. I'd probably be on some beach catching the rays. In any event, these are examples of dynamical systems that, unlike the first two, are quite unpredictable. The question is why? You say, I know why the weather and the stock market are unpredictable. Those are dynamical systems that seem to depend on just so many variables that it would be impossible for anyone to know all of the variables at any one time so as to make a prediction. For example, to predict the weather, you would have to know all elements of the weather around the globe instantaneously. You'd have to know the barometric pressure, the wind speed, the wind direction, everywhere on the globe in order to predict what the weather will be like a week hence. Similarly, the stock market. To predict where the stock market will go, theoretically at least, you have to know the behavior of all elements of the economy, of all consumers in the economy. Clearly, these are systems that depend on just too many variables to make a prediction. Well, it's certainly true that the weather and the stock market depend on many, many variables. On the other hand, that's not necessarily the reason it makes these dynamical systems unpredictable. It's one of the most remarkable discoveries of mathematicians in the last 15 or 20 years that very simple systems, very simple dynamical systems, systems that depend on only one variable, not millions of variables like meteorology or the economy, systems that depend on a single variable can behave just as unpredictably, just as turbulently as the weather or the stock market. That's what we'd like to talk about today, how very simple systems can behave in very strange and complicated ways. To simplify the situation, let's begin by talking about a mathematical dynamical system, a very simple abstraction of the kinds of dynamical systems that arise in nature. What's a mathematical dynamical system? Well, among the simplest of mathematical dynamical systems are the so-called iterated functions. Start with any mathematical expression, for example, the square root function, and start with any number, say x. How does one create a mathematical dynamical system? Well, through the process of iterating this mathematical function. That's accomplished this way. Take the initial number x, compute its square root, you get a new number. Then compute the square root of that number, you get a second number, and so forth, the square root of the square root of the square root. This is the process of iteration. It's a dynamical system. The numbers are changing in time. The question to the mathematician is, just as in the case of a scientist, can you predict what will happen? Can you predict what will happen when you iterate this function over and over again? Well, now you see that this process is ideally suited for use of a computer. There's nothing a computer can do better than iterate functions over and over again. So to illustrate that, I brought along my own home computer, rather homemade computer. This, you might recognize something that used to be called a calculator. I call it an iterator. An iterator comes with a bunch of numbers that you can input together with a bunch of functions which you can iterate. This iterator comes with the standard functions, x squared, square root of x, 1 over x, etc., and also with a quadratic function. So this is a fairly special iterator. How does one do the process of iteration? Well, with that square root example, let's start by inputting the favorite number into the calculator. For example, we might input 256. We then iterate the square root function by first pressing the square root button and then computing the square root of 256. That's 16. To iterate, we do it again. Square root of 16 is 4. Square root of 4 is 2. Square root of 2 is 1.41. And then we ask, what happens when we do this over and over again? Square root of 1.41. Keep hitting the square root button. Eventually you'll see that no matter what number you started with, you always end up with the number 1. So here's an example of an iterative process that's completely predictable. No matter what number you start with, when you iterate the square root function, you always end up with the number 1. Here's another example. Let's take the function x squared. Start with any number. Let's say we start with the number 2. When we iterate the squaring function, we get first 4. Square 4, get 16. Square 16, get 256. You can see what happens. Square 256, you get 256 squared, a rather large number. You see that upon iteration, repeated squaring, at least if you start with a number that's larger than 1, tends to infinity. So again, that's an example of an iterative process whose behavior you could predict. Here's another one. Let's take the sine function, the trigonometric sine function. What happens when you iterate the sine function? Well, let's start with any number, say 123, and then iterating. The sine of 123 is minus 0.45 in radians. Sine of that is minus 0.43. Take the sine again, minus 0.41. And you see what happens. Iterating the sine over and over again eventually yields, after 300 or more iterations, the number 0. So if you iterate the sine function, no matter which number you start with, you always end up with 0. Again, a perfectly predictable iterative process. One more example. How about cosine? What happens when you iterate the cosine function? Well, let's see. Let's start with any number, say 123. And what do you think happens when you iterate the cosine function? Anyone know? What happens when you iterate cosine over and over again? Well, it turns out that no matter what number you start with, when you iterate cosine in radians, you always end up with the number 0.73908. Where'd that number come from? Now, we'll talk about that in a minute. But for now, notice that you now know how to iterate, or what the result of the iteration of cosine will be. No matter what number you start with, when you iterate cosine, you always end up with that strange number. One last example. How about iterating the quadratic function 4x times 1 minus x? What happens when we iterate this simple quadratic expression? Well, let's start with any number, say the number 0.4. And what happens when you compute this quadratic expression? Now, if you plug in 0.4 to the quadratic function, you get 0.96. Iterate again, you get 0.154. Iterate again, you get 0.521. Iterate again, you get 0.998. Again, 0.008. Once more, 0.032. See the pattern? Try some more. Iterate again, 0.123. Iterate again, get 0.431. Do it again, get 0.980. Do it again, 0.078. See the pattern yet? Probably not. Iterate again, 0.288. Once more, 0.823. There is no pattern whatsoever when you iterate the quadratic function. That's because this expression is chaotic. That's because this function is totally unpredictable. For all intents and purposes, iterating 4x times 1 minus x is a random number generator. Okay, well, notice that most iterators don't come with a 4x times 1 minus x button, but that's no problem. Most computers do. You could very easily program a computer to iterate a quadratic expression, or in fact any mathematical expression, like 4x times 1 minus x. Here's a simple program to iterate the function 4x times 1 minus x. The program simply asks you to input your favorite number x naught, and then in this loop, we simply compute over and over again the expression 4x times 1 minus x, each time printing the result. After 100 iterations, we stop, and you see the first 100 points computed under iteration of 4x times 1 minus x. At this point, let me introduce some notation that we'll use later. When we iterate the calculator or the computer, that is, when we successively press the buttons on the calculator, we're computing what I call the orbit of the initial point. If we start with a number x0 and then press the button on a calculator, we produce a number x1. Press the button again, we produce x2. Press the button again, we produce x3. Successive pushes of these buttons yield the list of numbers that are the so-called orbit of the dynamical system. So the question in mathematics, akin to the question we asked in the beginning, is can you predict the fate of orbits of this dynamical system? Well, now let me interject some mathematics into all of this. Let me show you how you can predict the fate of simple orbits, of simple dynamical systems, by a procedure I call graphical analysis. For example, consider the square root function. I've drawn here the graph of the square root of x, and I've superimposed on this graph, the diagonal line, the line y equals x. How do I use this setup to predict the fate of orbits of the square root of x? It's easy. Suppose I start with a number x and ask for its orbit. Well, to compute the square root of x, what we do is simply draw a vertical line up to the graph of the function. When we reach the graph of the function, the y coordinate of that point is the number, the square root of x. If we now draw a horizontal line over to the diagonal, then we reach the point whose x and y coordinates agree. That is, we reach the point whose x coordinate is the square root of x. So how do we compute the square root of a number? Graphically, it's easy. We simply draw a vertical line to the graph and then a horizontal line back to the diagonal. So how do we iterate the square root function? We do this procedure over and over again. To compute the square root of the square root of x, we simply go to the graph and over to the diagonal. Iterate again. Go to the graph and over to the diagonal. Go to the graph and over to the diagonal. You see by this simple geometric procedure that iteration of the square root function via this staircase method leads you eventually to the point which lies at the intersection of the graph with the diagonal, and of course that's the point 1. No matter what number you start with, if we start out here with an x larger than 1 and go to the graph and over, go to the graph and over, go to the graph and over, inevitably we're led to the number 1. That is, orbits of the square root function always tend to 1, a process that we saw with the iterator a moment ago. A couple more examples. What happens when you iterate the trigonometric sine function? Well, let's see. I've drawn the graph here of sine x. Again, superimpose the diagonal y equals x. And again, let's start with any number whatsoever, say x, and iterate. To iterate, to find the orbit of x, we simply go to the graph and then over to the diagonal, to the graph and back to the diagonal, to the graph and to the diagonal. And again, you see that no matter which x you start with, when you iterate the sine function, inevitably you're led to the number 0. So iteration of the sine gives orbits which always tend to 0. One more example, cosine. Where did that strange number 0.73908 come from? Here's the reason for that number. Here's the graph of cosine. Here's the diagonal. Start with any x, say down here, and iterate by going to the graph and over, 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 to the graph and over. You see that, again, no matter which number x you start with, the orbit of x always tends to the point which lies at the intersection of the graph with the diagonal, and that point just so happens to be 0.73908. So again, there's a dynamical system, a mathematical dynamical system, whose orbits are completely predictable. What about the quadratic function? Well, the quadratic function has graph that looks like this. Here's the graph of 4x times 1 minus x. I've sketched it only between 0 and 1. What happens when you take a typical x between 0 and 1 and iterate? Well, graphical analysis gives the answer by going to the graph and over, 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 etc. You see that the orbits of 4x times 1 minus x bounce randomly around the unit interval, bounce randomly around the interval between 0 and 1. So this is an example of a chaotic dynamical system. The orbits of this simple dynamical system are, for all intents and purposes, unpredictable. So this harkens back to what I said in the beginning of the lecture. Here is a dynamical system that, unlike the weather or unlike the economy, depends on only one variable. Yet, despite the fact that the expression is so simple, the orbits, the dynamics, are completely unpredictable. This is the major discovery in mathematics, or one of the major discoveries in mathematics in the last 15 or 20 years. Now, as a mathematician and a mathematics instructor, can't possibly give a lecture without assigning some homework. So let me ask you to predict the orbits for various quadratic functions. I've listed here a bunch of simple quadratic functions, all of the form a constant times x times 1 minus x, and I ask you to predict the orbits for these functions using either the iterator or the computer or graphical analysis. The first two are easy. 1x times 1 minus x and 2x times 1 minus x. The orbits of these functions, at least for x's between 0 and 1, you'll see always tend to a fixed number. On the other hand, the next two, 3.1x times 1 minus x and 3.4x times 1 minus x, yield slightly surprising behavior. When you iterate this function, 3.1x times 1 minus x, all orbits tend to cycle back and forth between two different values. If you use 3.4 as the value of the parameter and iterate that function, all orbits tend to cycle back and forth between 4 different values of x. This is actually the beginning of what's known as the period doubling route to chaos, another of the very important discoveries in dynamics in the recent decade. Last problem is for you to iterate a constant times x times 1 minus x, where the constant is in the range 3.6 to 4. It turns out that there are very many values of the constant in that range, though by no means all, for which iteration of this function is practically indecipherable. Very few people on Earth know what happens when you iterate a constant times x times 1 minus x, where the constant is in this range. It's a fascinating problem that was only solved by mathematicians in the last 4 or 5 years. So there are some homework problems for you. Now let me move to some of the most interesting dynamical systems that do not depend on one variable, like the previous examples, but rather depend on 2 variables. Many dynamical systems, as we know, depend on lots of variables, so it's natural to look at dynamics in a higher dimensional setting, in this case, in the plane. There are very simple examples of dynamical systems with their orbits that occur naturally in the plane. One such dynamical system is simply the act of translation. A dynamical system is defined by moving points, say 1 unit to the right in the plane. For example, then, an orbit of this dynamical system would be, say, if we start with this red point in the plane and translate 1 unit to the right, translate again, translate again. That's the operation of iterating the translation function, and you see here the orbit of that point under translation. Another example of a dynamical system in the plane is the operation of rotation through a fixed angle. If we rotate points through a fixed angle and then iterate that procedure again, we produce orbits in the plane. For example, if we start with this point in the plane and rotate, we get this point. Rotate again, we get this point. Rotate again, you see that these points move around in the plane, tracing out the, again, so-called orbit of these dynamical systems. Now, both of these examples, translation and rotation, are hardly chaotic dynamical systems. You can very easily predict what will happen to the orbits of each of these dynamical systems. So let me pause now and explain exactly what I mean by an orbit that's chaotic as an orbit in a dynamical system in the plane. What do I mean by a chaotic orbit? Well, let's start with any dynamical system. Doesn't matter what it is. Suppose we have a dynamical system whose orbit, or one of whose orbits, looks like this. Start at z0, iterate, iterate again, iterate again. Maybe this orbit will cycle down to some fixed point in the plane. What does it mean for this orbit to be chaotic? Rather than tell you what it means for that orbit to be chaotic, let me tell you at the outset what it means for this orbit to be the opposite of chaotic, that is stable or predictable. This orbit is predictable if whenever I take a nearby orbit, say this orbit that I've colored red, the orbit of W, whenever I take a nearby orbit, the new orbit behaves in essentially the same manner. Orbits that have this property are called stable or predictable. Stable orbits turn out to be the good orbits, the nice orbits in a dynamical system. Stable orbits are the orbits that have the property that any nearby orbit behaves essentially in the same way. Why are these the good orbits? Well, for one thing, if your dynamical system comes from some physical system, meteorology, the economy, whatever, then whenever you try to measure exactly where you are in that system, whenever you try to measure the initial point z0, you're always going to make a mistake. You're always going to be off by a little bit. For example, you might be at the point w0. If your orbit is stable, that doesn't matter. When we iterate the orbit of w0, essentially the same thing happens. So orbits which are stable are not susceptible to initial observational error. Similarly, if you are using a computer or a calculator to compute the orbits of your system, your computer will always make numerical errors, will always make tiny round-off errors. So in computing the orbit of z0, you'll make a small numerical error, which will throw you off the orbit that you're looking at, possibly onto the red orbit of W. If that's the case, and the orbit of z is stable, there's no problem. The orbit, the red orbit of W, converges to the exact same place, and you can predict the behavior. So orbits that are stable are the predictable orbits. Orbits that are stable are the good orbits in a dynamical system. So what are chaotic orbits? Well, chaotic orbits are exactly the opposite. This same orbit in a dynamical system would be chaotic if this orbit does something, but arbitrarily close by there's another orbit, say again the red orbit of W, which behaves dramatically differently. Notice that the orbit of Z simply converges down to some fixed point in the plane, whereas arbitrarily close by, the orbit of W goes far out to right field. So this is an example of an unpredictable orbit. Make a small error in your initial condition, and the resulting orbit behaves vastly differently. This is the hallmark of chaos. This is the hallmark of unpredictability. So, for mathematicians, the natural question is, how large is the set of chaotic orbits? Is this a set that we can avoid in the plane, or is this a set that pervades everything? For the kinds of functions, for the kinds of mathematical expressions I'm interested in, that is, functions in the complex plane, the set of chaotic orbits has a name. It's called the Julia set. This set is named for the French mathematician Gaston Julia, who in the 1920s made extensive studies of the properties of the set of chaotic orbits for complex functions. It's one of the great tragedies in mathematics, I think, that if you read Julia's old papers, you see that he really understood the intricate structure of these Julia sets. He really knew how fascinatingly complex they were. Yet, he never had access to a computer, or especially computer graphics, to show the rest of the world how beautiful these sets were. As a consequence, the study of Julia sets languished after Julia's pioneering work until a computer came in the late 70s and showed us just how beautiful and interesting these sets are. In any event, the question for the mathematician is, how large is the set of chaotic orbits? How does it change as we vary parameters? What I'd like to show you now is an answer, at least a partial answer, to those questions. To answer these questions, I'd like to make use of what I consider to be an amazing theorem. This theorem allows you to compute this Julia set, the set of unpredictable orbits for a dynamical system. It allows you to compute it because it relates it to another set of orbits that's completely computable. For certain functions in the complex plane, the Julia set, the set of unpredictable orbits, is simply the same as the set of orbits that escape. It's simply the same as the set of orbits which iterate off to infinity. Now, I must say that this theorem is true only for a very special class of functions. It's only true, for example, for the trigonometric sine or the trigonometric cosine or the exponential function. It's very definitely not true, for example, for polynomials like quadratic functions. But there's another algorithm or another theorem which gives you a characterization of the Julia set. My purpose is I'm going to stick with the sine or the cosine or the exponential, so I'll make use of this amazing theorem to capture, to find the Julia set using computer graphics. So my goals are to show you that the Julia set is often a fractal. I'll show you also that the Julia set may literally explode as we vary parameters. And finally, I'll show you that the Julia set may sometimes behave in a very rhythmic, pulsing manner. How do we compute the Julia sets? Well, the algorithm for computing the Julia sets makes use of the theorem we just mentioned. Here's an outline of the algorithm. What we'll do is start with a square in the complex plane and fill it with a grid of points, maybe 400 by 400, or if we have lots of computer money, 1,000 by 1,000. And then we'll iterate each point in this grid. Now, during this iteration, one of two things can happen. Either the point can fly off to infinity, in which case, by the amazing theorem, we think the point is in the Julia set, or during the iteration, the point never goes far away. It always stays close by. In that second case, we're not in the Julia set. We're in the set of stable orbits. So here's what we'll do. If, for example, we start with a grid point here and iterate that point, compute its orbit, and find that it escapes to infinity, then we'll color that point. So colored points in the images you're about to see are points that are in the Julia set. On the other hand, if when we iterate this function, if we start at a grid point, say here, and iterate and find an orbit that, well, perhaps is periodic, whatever, or does not go off to infinity, then by the amazing theorem, that's not a point in the Julia set, so we'll leave it black. So black points are points whose orbits are stable. They're not in the chaotic set. Colored points are points whose orbits are unpredictable. They are in the Julia set. What do the colors mean? Well, remember, we color a point if its orbit escapes at some iteration. So during the iterative process, if an orbit escapes at iteration number I, then we'll color code the initial point on that orbit with a color that depends on I. So points that you see, which are red or orange, are points whose orbit has escaped after a very few number of iterations. They escape very quickly. Points that are yellow or green take a moderate amount of iterations to escape. Points that are blue or violet take a long time before they escape, 100, maybe 200 iterations, but escape they do, so they're in the Julia set. The point is that any point that's colored is a point in the Julia set, whereas any point that's black is a point that's not in the Julia set. Now let's turn to the computer graphics. I'd like to begin by showing you some Julia sets that literally explode. I'll show you the Julia set of a constant times the exponential, which explodes when that constant is exactly the number 1 over e, 1 over the base of natural logarithms, 1 over 2.7128. Another example, I'll show you a complex constant times sine. That Julia set will explode when the parameter c is 0. That is 1 sine z has Julia set that's literally waiting to explode. Similarly, there will be an explosion in the cosine family, and then finally another one in the complex constant times the sine family. So let's turn now to the computer graphics. What you're looking at here is the Julia set for the function 1 over e times e to the z. This Julia set is an example of a fractal. By that I mean the following. Notice that this Julia set basically looks like a fist with infinitely many fingers attached. The red area looks like a fist with lots of fingers dangling from it. Now look at any one of the fingers. Magnify any one of those fingers and you see that it too looks like a fist with infinitely many fingers attached to it. If we zoom further into one of these fingers and then magnify it, it looks like a fist with infinitely many fingers attached. So if we continually zoom into a portion of this picture, the colored portion of this picture, the Julia set, we see that under magnification it looks the same over and over again. This is the concept of self-similarity, one of the inherent portions of the notion of a fractal. The next slide magnifies the portion, the tip, of this Julia set. You see that when we magnify this portion of the Julia set, it too looks like a fist followed by infinitely many fingers, then a fist with infinitely many fingers. So the deeper you delve into a Julia set, the more you see the same structure over and over again. Now notice here, though, that almost the entire screen is black. Almost the entire screen consists of points whose orbits are stable. Only the small portion of this picture that's colored is the Julia set. Watch what happens when we change the parameter to be larger than 1 over e. The next slide is the Julia set for some constant larger than 1 over e times e to the z. What you see is the screen literally fills with color. There's an explosion in the Julia set. You say, well, I see some black in that picture. Actually, to compute this picture, I used only 75 iterations for the Julia set. If I had used more, that black would disappear. The next slide shows what happens when I use 250 iterations to compute the Julia set. Notice that that small black region has all but disappeared. Julia set pervades the entire plane. The chaotic orbits have all of a sudden exploded and become everywhere. This slide is the Julia set for the complex sine function. To orient you in the complex plane, notice that the real line runs right through the middle of the picture. The real line runs right smack through the middle of the picture with 0 right in the origin, right in the center. Notice that every point on the real line is colored black. We know why that is. Remember, when we used the iterator, we saw that every point on the real line under iteration converged down to 0. That is, they didn't escape. They're not in the Julia set. On the other hand, Julia set is above and below here in the complex plane. Note, too, that the Julia set for the sine function looks like, well, it looks like a pair of snowmen going up and down in the complex plane. This is an example of a fractal because let's zoom in to a portion of this pair of infinite snowmen. The next slide zooms in on the arm of one of these snowmen. Notice that it too resembles an infinite snowman. The next slide zooms in on a portion of that arm, and you notice that the arm comes equipped with infinite pimples, again resembling infinite snowmen. So the Julia set of sine z is the same under magnification. It too is a fractal. Now we're going to change the parameter. Instead of looking at 1 sine z, the next slide is the Julia set for the complex number 1 plus epsilon I sine z. Notice again that the snowmen disappear, the screen fills with color, the Julia set has exploded. Something has happened to the set of chaotic orbits. The next slide shows another Julia set. This is the Julia set for a complex cosine function. In fact, I times 0.67 times the cosine function. Change that parameter a little bit, and you get the next slide. The next slide is the Julia set for another complex constant times cosine again. The screen is filled with color, the Julia set has exploded, and if you're a mathematician, you smell a theorem nearby. One more sequence. The next slide shows the Julia set for 0.6 plus 0.8i sine z. In the trade, this is known as a Siegel disk. Change that parameter a little bit, just a small amount, and you get the next slide. The Julia set, again, explodes into color, only this time in a fascinatingly complex way. Let's investigate this picture a little bit. The next slide gives a magnification of a portion of this Julia set. Notice how intricately the colors are interwoven in this picture. The next slide shows a zoom on one of these spirals. You note that even among all of the complexity, we see some interesting patterns beginning to emerge. So the natural question is, what makes these Julia sets explode? Well, here's the answer that's only been found in the last 5 or 6 years. The reason Julia sets explode is the escape of the so-called critical values. Well, let me not explain exactly what I mean by a critical value. The critical values for the exponential function, for example, turn out to be the value 0. That's what's known as the asymptotic value. That's the omitted value. There's no number whose exponential is 0. Similarly, the numbers plus and minus pi over 2 are the critical points for sine. They're the maximum and the minimum of the sine function. They're the places where the derivative of sine, for example, is 0. So, the theorem, a recent theorem of Dennis-Sullivan, says that if all of the critical values escape for one of these functions, then necessarily the Julia set, the chaotic set, the unpredictable set, is the entire plane. Well, we saw that with the exponential function when the parameter went above the number 1 over e. So let's see why the exponential function had Julia set which exploded at the parameter value 1 over e. I've drawn here 2 graphs of the exponential function, a constant times e to the x, one in the case where the constant is less than 1 over e, and one in a case where the constant is greater than 1 over e. Notice that as we lower the parameter value c, the graph of the exponential function eventually decreases so that it's tangent to the diagonal and then pierces the diagonal. For c values larger than 1 over e, graphical analysis shows us what happens to the critical value for the exponential. The critical value is 0. When we compute its orbit, you see that if c is larger than 1 over e, the orbit tends to infinity. By the Sullivan theorem, that means that the Julia set must be the whole complex plane. On the other hand, when c was less than 1 over e, note that the orbit of 0 is trapped, can't possibly go to infinity. The Julia set is not the entire complex plane, and we saw that illustrated dramatically with the computer graphics images. Let's try to see these explosions in the complex sine function. What you're looking at is the Julia set for 1 sine z, And remember, the critical points for the sine function occur at plus and minus pi over 2. In the complex plane, plus pi over 2 and minus pi over 2 are right here in the belly buttons of the infinite snowmen. Watch what happens when we change the parameter from 1 to 1 plus epsilon I sine z. The next slide shows the Julia set for 1 plus epsilon I sine z. I've computed this Julia set using 35 iterations, only 35 iterations. That means that if a point is colored violet, that point necessarily escapes after about 35 iterations. And notice what's happened. Plus and minus pi over 2. The former belly buttons of these snowmen are colored violet. That means that the critical points have escaped, so the Sullivan theorem says that the Julia set must be the entire complex plane. Let's see that by computing the same Julia set, iterating not with 35 iterations, but with more. The next slide shows the Julia set of the same function computed not with 35 iterations, but rather with 75 iterations. Notice that the whole screen is almost entirely filled with color. The black regions have really shrunk. The next slide shows what happens when I compute the same Julia set with 150 iterations. The black region is shrunk some more. If I use 500 iterations, I get the next slide, and you see that the black region is practically non-existent. The whole screen is filled with color. This confirms Sullivan's theorem. The Julia set is indeed the entire complex plane. Chaos is everywhere. Now, when students who work with me at Boston University saw pictures like this, their minds immediately went to Hollywood, and they said, let's make a film of these Julia sets. Well, we didn't quite make a film of the sequence you just saw. Rather, we made a film of changing the parameter value in the complex sine continuously. The next slide shows where we began. The next slide is the Julia set in magnification for 1 sine z. Now, keeping the number of iterations constant at 35, we change the parameter continuously in the family 1 plus epsilon I sine z. The next slide is the Julia set for 1 plus epsilon I sine z. The next slide is 1 plus 2 epsilon I sine z. The next slide is 1 plus 3 epsilon I sine z. You see that there's some motion going on in these spirals as we vary the parameter. The next slide is 1 plus 4 epsilon I sine z. What your eye is missing is actually the most spectacular part of the film that we eventually made. The next slide is 1 plus 5 epsilon I sine z. Again, your eye is missing the most interesting behavior. Then finally, 1 plus 20 epsilon I is the next slide. As you see, the Julia set has eventually evolved to become the entire complex plane. So now let me show you what this motion looks like on film. What you're looking at is the Julia set for sine z. Remember the infinite snowmen. Now let's vary the parameter continuously. 1 plus epsilon I sine z. The Julia set explodes there. Boom. The screen fills with color. But now notice the fingers attached to these spirals. Notice how they slap each other. There. And there. And as we zoom in the complex plane, we see that occurring over and over again. That's something we didn't see in the still pictures, and in fact is something that's very interesting mathematically. Let's see that by panning over the plane down to the critical point for sine, the point pi over 2. Watch what happens at pi over 2. We see the birth of a little black region right there. Stable orbits are born as these fingers cross each other. Now let's turn to the explosion in the cosine family. I times a constant times cosine, and there's a close-up of the explosion done as only Hollywood can do it. Here are the stars of the show. Start at 0.65 I cosine. After the explosion, the screen is filled with color. So here's the motion. The Julia set explodes right there. Again, the screen fills with color, but notice in the cosine family that the fingers attached to these spirals don't cross. There's something different between the sine and the cosine. Now we're up to 0.8 I. Let's take a right-hand turn in parameter space and increase the real part of the constant. So look at epsilon plus 0.8 I, and notice what happens right in the center of the picture. Little black regions appear and disappear. What we seem to see are fingers crossing each other. Now let's zoom in right near 0 in the plane, the critical point for cosine, and watch the fingers cross each other again. As we increase the real part, epsilon plus 0.8 I, notice how little black regions open up and then close down. So we've seen that when the critical orbits escape, the Julia set explodes. What I'd like to show you now is what happens if the critical orbit seems to escape but then returns. For example, what happens if we have a graph that looks like this? The critical point. The critical orbit is the orbit of this point here. Notice that it's a minimum for the graph of the function. When our graph looks like this, the critical orbit does not escape. However, if we raise the graph just a little bit, if we change parameters so that the graph lifts off the diagonal, then we see that the critical point can apparently escape, but then return. So the next situation we'd like to study is what happens if this critical point apparently escapes, but then comes back. It turns out that lots of different dynamical phenomena can occur. For example, we may get stable orbits. Remember, in the computer picture, this means black regions. Here's an example of a stable orbit. If we lift the graph just the right amount, we may arrange for the critical point to iterate far away, but then return exactly to itself. If the critical orbit turns out to return exactly to itself, that is, if the critical point is periodic, turns out that we must have a stable orbit nearby. We must have black regions in the computer pictures. Now, if we change the graph of this function oh so slightly, by raising it just a bit off the diagonal, we may be able to arrange for the critical point to iterate far away, take a long time to iterate far away, but then again return exactly to itself. That means we can produce the critical point being of higher period and another different black region. There's other kinds of behavior. For example, we may be able to produce aperiodic behavior. We may be able to produce a graph such that the critical point iterates far away, but then returns not to itself, but rather cycles back through the original funnel. Or we may be able to arrange a graph for which the critical point iterates far away and then gets stuck and never returns. So there's all sorts of different possibilities for the dynamical behavior associated to the critical point escaping, but then returning. Let me illustrate this with the family of constant times cosine z. Here's the graph of a constant times cosine z, where the constant starts at pi and decreases down to just below 2.97. Notice that the graphs for a constant times cosine do exactly what I just said. They start here with pi cosine z. At approximately 2.97 cosine z, the graph is just tangent to the diagonal, and then thereafter the graph lifts off the diagonal, so this critical point, this minimum, can escape but then return. So all of the images that you're about to see occur for the family of constant times cosine, where the constant varies from simply pi down to 2.97, and in the computer experiments we should see the birth and death of lots of these black regions and all sorts of other stuff. What you're looking at here is the Julia set for pi cosine z. Notice that it consists of a huge black oval together with satellite black ovals all around. These are the stable regions for this Julia set. The colored regions above and below form the Julia set. Now let's vary the parameter. The next slide shows the Julia set for not pi cosine, but now down to 2.97. The black oval folds up into a cauliflower-shaped region. This is the point where the critical point's about to escape, but then return. The next slide shows the explosion about to happen. Here I've caught the explosion in mid-explosion. Color begins to leak into the black basin, and the next slide shows what happens after the explosion. Color pervades the entire basin. This slide shows that there's an interesting and different pattern to the Julia set. Notice that the black regions seem to be little black bubbles that aren't disappearing as we vary the parameter. Note in particular the two black bubbles right in the center of the picture. Watch what happens as we vary the parameter. These two black bubbles will come to the center, coalesce, and then separate on the vertical axis. The next slide shows that. Now look at these black bubbles. Look closely at them. You see that they too are about to explode. Let's look at that more carefully by zooming in. The next slide shows what happens when we zoom in on that central meeting point. Notice that what had been black bubbles are now colored. They resemble, in fact, the original picture. This, again, is the fractal nature of these Julia sets. The next slide zooms in very closely on what's happening near the central point in this picture. Two of these former black bubbles are about to coalesce as the parameters change. The next slide shows these black bubbles colliding. They interact in a very complicated way as seen in the next slide. And there seem to be lots of explosions as you see in the next slide. And then these black bubbles separate and go up the vertical axis as you see in the next slide. Now what you should realize is that all of this motion is taking place in the parameter region between 2.97 cosine and about 2.94 cosine. There's a tremendous amount of activity that's occurring in the dynamics for this small interval of parameter values. Now let's put all of this motion together and see what happens on a film. So here's the motion. Start at pi, down to 2.97. There's the explosion. So let me slow the parameter down and watch what happens. Notice how these little black bubbles run around the screen in a fairly intricate fashion. Now notice that these black bubbles aren't black at all. that in fact there's color inside them, that they too explode. So let me slow the parameter down again and zoom in on what's happening near the center of this picture. Notice now how the small, formerly black bubbles actually resemble the whole picture. As we zoom in, we see the same thing over and over again. What mathematicians have discovered is actually fairly remarkable. Each time two of these black bubbles coalesce at the center of the picture, the parameter is actually running through what's known as a Mandelbrot set. And all of the intricacy that's associated with a Mandelbrot set is actually occurring over and over again as these bubbles collide. Now, as we pan over the plane, notice that the same activity is occurring everywhere we look. Your homework problem is to explain what you're seeing.